In this short presentation, we will discuss an article which appeared in AOPA by Catherine Cavagnaro, where she discusses where Vy occurs and how best to operate on the back side and front side of the power curves. This is an outline of the presentation, so please feel free to pause the video and review the items and resume when you're ready to continue. There are multiple v-speeds with which a pilot must be familiar. However, prior to departure, two which must be considered include the best angle of climb or best rate of climb. The choice depends on the height and proximity of obstructions near the departure end of the runway. While Vy is generally preferred as an initial climb speed, if there were tall objects beyond the departure end of the runway, it may not provide enough altitude to clear them. In that case, Vx, or best angle of climb, would be preferred in order to gain the greatest height in the shortest distance. This presentation, however, will focus on best rate of climb, or Vy, and how it divides the back side and the front side of the power curves. We are all familiar with the idea of how drag increases when a car moves faster and faster along a road. This is similar to what occurs in an aircraft when flying at a faster and faster speed. We can experience the same force as the umbrella pushes against the wind. This type of drag is termed parasitic and has multiple components which are discussed in a separate presentation. There is another drag which is unique to an airfoil and occurs anytime lift is being created. Unlike parasitic drag, which increases as the airplane increases its airspeed, this drag, known as induced drag, increases as the airplane slows while maintaining level flight. This vector diagram demonstrates an airfoil and the forces generated when lift is created. In order to maintain level flight, the wing must develop a vertical component of lift which opposes the weight of the airplane. However, as the wing is generating lift, it's also creating drag. This is a smaller vector pointing towards the left. The total lift vector, then, is the sum of these two components. Another concept which will be very important to understand is relative wind and angle of attack. Relative wind refers to how the oncoming air strikes the wing as it moves along its flight path. The angle of attack is the angle formed between the relative wind and a portion of the wing called the chord line. The formal definition of the chord line is discussed in a separate lecture. However, for our purposes, consider this to be the undersurface of the wing itself. In this animation, notice how the angle of attack increases as the nose is pitched up and the airplane maintains a level flight path. One can imagine how induced drag is increasing as this angle of attack increases. If we plot the two types of drag against airspeed, we obtain the drag curve. The point where the total drag is minimum is called L/D max, which corresponds to the airspeed where the ratio of the lift to drag is the greatest and also represents our best glide speed, but is not Vy. Also notice how parasitic drag increases exponentially as airspeed increases, whereas induced drag increases with decreasing airspeed. Vy is the airspeed which will provide the best rate of climb, or said differently, maximum height in the shortest time, and depends on the amount of excess power available over what is required for your current flight condition. For this presentation, we will simplify the lift equation and consider lift to be proportional to the speed of the air over the wing multiplied by the coefficient of lift. The coefficient of lift depends on the design of the wing and is generally determined experimentally using a wind tunnel. The purpose of this animation is to illustrate how the angle of attack is nearly directly proportional with coefficient of lift and has an exponential relationship with coefficient of drag. For practical purposes, we can replace the coefficient of lift variable in the above equation with angle of attack. When the wing exceeds the critical angle of attack, it can no longer produce enough lift to oppose the weight of the airplane, and it will begin to sink. This is commonly referred to as the stall. Here we have an altitude speed map showing lines of constant energy. At any moment during flight, your airplane has a fixed amount of energy which, ignoring fuel, depends on its altitude or potential energy and its airspeed or kinetic energy. The opposing forces are parasitic and induced drag. For a fixed power setting, you can trade altitude for airspeed and vice versa, but your total energy remains the same. In other words, you can choose to speed up and descend or slow up and climb. To begin our discussion, we will keep flaps up, cowl flaps open, ailerons neutral, and use the rudder to maintain coordinated flight. The two variables to the pilot are the throttle or power, and the elevator to adjust the angle of attack. This graph illustrates how vertical speed in feet per minute varies with airspeed, or angle of attack, with a fixed power setting. In other words, there is no change in the total energy of the system. The airplane in this particular configuration has a best rate of climb which occurs at an angle of attack of 7 degrees. The dashed horizontal line represents the airspeeds dividing the positive rate of climb and negative rate of climb, in other words, descent. The plane begins with a 1 degree angle of attack corresponding to a descent at a particular airspeed. As the angle of attack is increased by back pressure on the yoke, it begins to generate more and more lift, and at about 4 degrees, it could sustain level flight. As the nose of the plane is increased further, it begins to climb at the expense of decreasing airspeed. At that airspeed corresponding to Vy, we have the best rate of climb in this configuration. Next, as back pressure is further increased on the yoke, the angle of attack increases and airspeed decreases due to increasing induced drag. Between 7 degrees and 12 degree angle of attack, we are still ascending, though at a gradually decreasing rate of climb up until about 12 degrees. Thereafter, any further increase in angle of attack will result in a nose-high descent. If the critical angle of attack is exceeded, the plane will stall and sink rapidly. This slide demonstrates the effect power has on vertical speed. As power increases, the airspeed, think angle of attack, at which Vy occurs is shifted toward the right. Also, for any given airspeed, the addition of power will always result in a higher climb rate. The opposite is also true. Finally, note at idle power there is one airspeed which will result in the minimum sink rate, VMS, which is not the same as best glide speed. Now let's look at some practical applications of operating on the front side and back side of the power curve. In the first case, we are on the front side of the power curve, in level flight, and trimmed for a constant airspeed with an ATC assigned altitude of 4,500 feet. At some point, an upward gust lifts the airplane to 4,800 feet. Since you need to descend back to your assigned altitude, you have two choices. Your current airspeed requires a 4 degree angle of attack. You could descend by pitching nose down, which would result in an increase in airspeed, and as you near your assigned altitude, pitch back up to the previous angle of attack, think sight picture, and continue flight as before. Or you could decrease power and allow the airplane to descend at constant airspeed. As you approached your desired altitude, you would add back the power you removed, and you should be close to the same configuration you had before the gust. In this next case, you are slowed down to enter the traffic pattern at 1,000 feet AGL when a gust raises your airplane to 1,300 feet. What is the best option to return to your previous altitude? Let's look at three possibilities. Let's say your current airspeed requires a 12 degree angle of attack. If you were to try and correct the altitude excursion only with yoke, what would happen? Well, if you pull back on the yoke to increase the angle of attack, the airplane would slow and begin a descent. However, you are near to the ground and close to the critical angle of attack and risk for stall. Alternatively, you could pitch forward, which would result in a descent, but you would also be accelerating toward the ground in a nose-low attitude. Pretty scary. What about using power? By decreasing power, you would begin a constant rate descent just as you did on the front side of the power curve. If, on the other hand, you experienced a downdraft, you could regain altitude at a constant airspeed by increasing power. So, in summary, as most of our flying is done at cruise speeds, that is, on the front side of the power curve, it is easy to manage altitude excursions using the yoke, throttle, or combination of both. However, as you slow to below Vy, or the backside of the power curve, managing altitude deviations exclusively with the yoke can place the aircraft in a dangerous flight condition. In this article, Catherine Cavagnaro explains that she teaches her students at an airspeed used for cruise climb, or ones used to descend toward the pattern, both above Vy, it makes sense to hold a fixed airspeed using the elevator and let the throttle or power govern the vertical speed. For a more detailed discussion on overall airplane energy management, see our lecture entitled Energy Management, Mastering Altitude and Airspeed Control. We hope this presentation gave you a better understanding of Vy, as well as operating on the front side and back side of the power curves. Thanks for joining us, and remember to fly smart and stay safe.